Let's test the subsystems of a quadratic integrate and fire. The first one is an inverting integrator. And what I'm going to do is go give it a -1 and a +1 constants so that I should get positive and negative ramps. Easiest way is just to see it. Okay. And you can see that the input, right, when the input is positive, it's got a negative slope. When the input is negative, it's got a positive slope. And then I can, if you find that slope, right, it'll be around 237, okay, which is the slope of 1 over 42, 4.2 milliseconds. Now, once you do that, you want to add your initial condition or your V reset. In this case, I wanted it to be -1, so I add another inverting amplifier, one with a gain of 1. So now my integrator is it's non-inverting, and then I add a -1 by putting the power supply into a gain stage that makes me have a 1/5 gain or a -1/5 gain, which will give me a -1. So I'll have my integrator -1, and if my integrator goes to 0, anyway, it's just easier to see it. All right. So here's the output, and here's the input, and notice it's inverted. This is going rail to rail, and now instead of going to 5 volts, it's only going to 4. I'm subtracting 1 volt. Now, why doesn't it go to -6? That's because I can't go below 5, which is the negative power supply rail. The next subsystem is the Schmidt trigger, and notice that the feedback is coming here on the positive node, right? And what this is going to do is the circuit's going to act, it's going to have a switching threshold in 2 different places, all right? And that's, so the high to low and the low to high will occur at 2 different places. That's because there's a memory element inside. Memory can only be done with transient, right? So I'm actually running, all right, I'm just going from -2 to 2 and back down. And you can see it switches here and it switches here. And it's not symmetric about this point. So that is part of it. But it's better to change the x-axis to Vn. And now you can see when it goes from this way, it's going to switch here. When it's coming this way, it's going to switch here, which is at -1 and 1 volt. And this is the hysteresis window. And that is, now I can move this window back and forth by adding or subtracting a voltage here. All right. The equation is in the lab manual. So this one does need a transient to get it to work. Now the multiplier, we can do a DC sweep of the input, and we just look at x squared. I'm going to plot x squared, and that looks pretty squared. But really, if we can see a straight line by taking the square root of it, that'll be a little bit easier to check. But you can't take the square root of a negative number in LT Spice, so we take the absolute value and then take the square root. And now we can kind of see this almost perfect straight line. And yeah, there's a little something going in here. That's just a simulation artifact, not to be worried about. So anyway, those are the main subsystems of the quadratic integrate and fire. And then the next thing to do is to put it all together. And here's the inverting. Here's another inverting, adding in the initial condition. Here's a Schmidt trigger, which then controls these two PMOS transistors, which are tied here. So whenever this goes, whenever this switches to a high voltage, these turn off, and then it just integrates. When it goes low, these PMOS tie that node and that node to 0, and it discharges the capacitor and resets the integrator. You can just look up resettable integrator. That is how you test the subsystems of your quadratic integrate and